Okay, let's take a peek at something fundamental in section 1.4, and it's dealing with, hey, we're going to multiply a matrix with a vector, okay? This is based upon a definition, okay? But the definition um, makes sense, and so we use it, just like the definition of all of mathematics. Anyway, there is a definition, and what I've got is you can look at this as a vector, a matrix that is 2 by 4 multiplying with a vector, right? So the way it's defined to go, okay, by definition, is that it is equal to, okay, the top number 1 times the vector 2, 1, the first column. So the first term in the vector multiplies with the first column, okay, like it's a scalar times a vector. You keep going. So minus 2 times minus 1, 3, plus, in this case, it's going to be plus 6 times the third column, 4, negative 2, and then finally plus 3, fourth column is 0, 8. This is a definition. Let's see what we got. Well, you can see it's a sum of 4 vectors that are 2 by 1, so we're going to get a vector that's 2 by 1. So let's take a peek at this, and what we've got is, let's put it all together. It's going to be 2 plus 2 plus 24 plus 0, okay? Do you see what I'm doing there? I'm just putting all the top guys together and now all the bottom. 1 times 1, minus 6, minus 12, and plus 24. And the net result above is 28. Do you see that? And bottom is that's 12, that's 6. I think I have a 7. And that's it. You multiply the matrix times the vector and you get a new vector, okay? Now there's a more common way to do this, by the way, and that's what I want to highlight next, okay? You know, this is a good way, that's by definition, but mostly what people do is they go row by column, and it's a little bit more straightforward, only to make life easier, but the ultimate definition is what we just went through, and that helps us in theory later. Okay, in this case, we do it another way. Do I have something about, no, I don't, okay. I'm going to do the following. I'm going to multiply this row times this column. It's like a dot product if you've ever experienced that. So what I mean by it is we're going to have the 2, how do I write? I'm going to write it this way. It's going to be a matrix. It's going to be 2 times 1. Let me erase this stuff. In fact, how about I just write it larger? So I will. All right, so it's equal to 2, negative 1, 4, 0, 1, 3, negative 2, and 8 times this vector again. We're going to get the same result a different way. Okay. And the result the way we're going to do it is we're going to take this row and multiply it with this column. Okay, and that's going to create a more, we'd call it a dot product in another class, and later we will call it a dot product, but it looks like this. It's going to be 2 times 1, I'll just write it out, minus 1 times minus 2, plus 4 times 6, and then finally plus 0 times 3, okay? What is that equal to? Well, we've seen this before. It's equal to 2 plus 2 plus 24 and plus 0, okay? So the net result is, we've seen those numbers, it's 28. Okay, so the story is, it's creating a vector a little more efficiently, okay? And then you do the same thing, maybe a different color, green maybe, and we're gonna have this guy also multiply with the vector. So the second row is gonna multiply with the vector, and we're finding 1 times 1, and then plus 3 times negative 2, and then minus 2 times 6, and then finally plus 8 times 3. Look at the symmetry of this. There's so much symmetry in matrices. Up here it's 1, 1, and minus 2, and 6, 6, etc. And we get, as a result, 1 minus 6 minus 12 plus 24, and I believe that's going to make our 7. Okay, pretty cool. So there's a point to this in a moment. At the very end of this video, we'll see it. But I do want to point out to you the size of these matrices. As we know, we count the rows and the columns, and this is a 2 by 4. And then the row here is 4, and the column, there's only 1. Okay, so there's something to observe. Okay, these numbers in the middle equal each other. Later, when we do matrices with multiplying together, that's an important topic. So they are equal. What that means is the number of columns in the matrix matches the number of elements in the vector. So we can actually take the product. If those two numbers don't match, you don't have a product. Secondarily, the outer numbers, the 2 and the 1, guess what? They actually tell you the size of your resulting matrix over here, which is 2 by 1. Okay, so this is a good thing to study. It's really easy, obviously, but the ramifications are pretty good. And I'll end right here by saying the following. Hey, you can take a matrix times a vector now, and let's say we know what we're doing. Let's say we go like, well, it's equal to A is like, this is column 1 of A, this is column 2 of A, dot, dot, dot. I don't know how many there are. Let's say there's n of them. And then over here, this would be whatever by n. Over here, this is I'm gonna write x as x1, x2, dot, 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 xn. And over here is some vector b, whatever he is, okay? And if you use the definition, it looks like this: x1, column 1, multiplied together, plus x2, column 2, plus dot, 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 plus xn, column n, is equal to b. And you know what? If you look at that more closely, you're actually looking at a system of equations. Because what if, for instance, column 1 looked like this: x1, and this column was a11, a12, a1m, I should say. Okay, I won't go too far in this, but it is a good thing to see 1m, x2. All right, I'll finish it. What we've got is a21, a22, a2m, let's say. And finally out here, xn times an1, an2, and dot, 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 am, and n. And in this case, now we know the size. If we gave it a letter B, we have a matrix. What we have here is B1, B2, Bm. Okay, and if you write that out, what you've got is a system of equations. You've got a number x1 times a number a11, plus, I forgot the plus in here, plus a number x2 times a number a21, plus plus xn, an1 is equal to b1, etc. And it's a new way of writing systems. Okay, so that's a good thing to see. And I think we'll stop it there.